ladies and gentlemen, welcome back for another round. We're going to be wrapping up our electrochemistry unit today. We're actually going to be taking a look at electrolysis and electrolytic cells. Now, I've got written on the computer screen here that these are your non-favorable reactions, and what that really means to you is that these are going to have a negative E cell value. Another large thing that you're going to have to be able to recognize with these things is that you must use a power source to drive these reactions. Since it is a non-thermodynamically favorable process, it is not spontaneous. We will have to actually use energy to drive and make this reaction happen. All right? Voltaic cells, those are battery, right? Those are our galvanic cells. Those are batteries. They happen spontaneously. Electrolytic cells, they need batteries to actually be driven, right? And so that's a big point that you want to make sure that you get your head wrapped around before we even get any further. Electrolysis and electrolytic cells, these are non-thermodynamically favorable reactions. They have a negative E cell value. They must be driven by a power source to get the reaction to occur, right? In other words, we need batteries, all right? Another big difference, and I'm actually going to write this one out, is that our voltaic cells, and I'm calling them voltaic, they can also be referred to as galvanic. So our voltaic cells, they have half reactions that are physically separated. And so I'm going to say that are separated. So those are physically separated. Electrolytic cells, we do not separate them. Electrolysis can occur all within the same reaction container. And so that's another big point that I want you to get down real big. Electrolytic cells occur within the same reaction. And so if I was going to draw an electrolytic cell, I'll put two different color electrodes here. And then let's give ourselves a wire, right? And then over here on the side, I'm going to have a power source. And so notice on this, let's finish that out. So I don't know what that is. Let's go. There we go. So our power source, right? And it can occur either in an aqueous environment or it will occur in a molten ionic. Otherwise, in other words, I'm going to melt down an ionic compound. And so those are our two main scenarios. It's either going to be aqueous with water or it's going to be a molten ionic where I've just got a pure substance in there that I'm melting and trying to purify. You know, a lot of our ores and things like that will use this electrolysis to actually separate the ores out and to purify our metals, all right? And that's something that we can get into what that actually looks like in our problems and things like that. But definitely, I want you to understand all of our mnemonics still work for this, right? The red cat, fat cat, our reduction still occurs at the cathode. Our oxidation still occurs at the anode. And so what you'll do is you'll have on this, you'll actually have just one of the particular electrodes will function as the anode. The other electrode will function as the cathode. All right? And you'll have to be able to label those. But the big thing I want you to see is that we've got to have this power source to drive this reaction. So if you're ever looking at a cell and you're trying to figure out, hey, is it galvanic or electrolytic, if you see a power source, you'll have to understand and be able to spot recognize that that is actually an electrolytic cell. You would expect to get a negative E cell value out of that. All right, and so moving on now, I've gone ahead and I've erased everything, and what we want to do now is we want to take a look at Faraday's law, and I paused the video and wrote it down because it's a rather lengthy definition here, but I wanted to get you the exact definition of Faraday's law here. All right, and so Faraday's law is that amount of substance being oxidized or reduced at each electrode during electrolysis, right? Remember, this is my non-thermodynamically favorable process where I still have oxidation and reduction. It's directly proportional to the amount of electricity that passes through the cell. Remember, we said we were going to have to input this power to drive this reaction, and so the amount of reaction that occurs, it should make sense, is directly proportional to the amount of energy that I put in. Right? If I put in energy for a longer period of time, if you will, I'm going to get more of my substance oxidized and reduced. If I put in larger amounts, like a larger voltage or a larger amperage, I'm actually going to get more stuff oxidized and reduced. And so that should actually make sense since I'm actually using the energy to drive the reaction, right? The more energy I put in, the more of a reaction I'm actually going to get. So what I want to do now is I want to take a look at a couple of units. The first one is a volt, and for these kinds of calculations that we're going to run into, I need you to understand the breakdown of these. A volt is actually a joule per coulomb, and so with this, a coulomb, this is essentially an amount of charge, and then your joules here is the work that's needed to actually push the charge through. All right, and so coulombs is that C is an amount of charge, and then joules is the work needed to actually push. So what voltage actually tells us here is it's essentially how much force is needed, how likely are these electrons, or how attracted are these electrons actually flowing from one place to another. All right. The other one we would need to take a look at is an amp. So 1 amp, this is current of electricity, right, or an amount of electricity here. We're going to see is equal to 1 coulomb. And I guess I could just leave that as a C. So 1 coulomb per second. So an amp is an amount per time, right? How much charge per time am I pushing into my particular cell? And then the last one is we know is Faraday's constant. And what it means is that there are 96,485 coulombs of charge per mole of electrons. All right? And so what we're going to be able to do with this kind of stuff, ladies and gentlemen, this is essentially just dimensional analysis and a little bit of stoichiometry, is to be able to use this information because everything's directly proportional to the amount of electricity that passes through there. I can relate it to, hey, how many moles of metal am I going to get out? How long will it take? How much energy do I need to actually put in if I'm starting with this much? And so it really just turns into a stoichiometry problem. And I do want to give you just a general flow of information, and so I'm going to go ahead and put a kind of a stoichiometry map down here, if you will, almost. All right, and so what I've got here is just my general flow. You probably want to pause this and get this down real quick before I move on, because I'm going to explain a couple of things. And so going from grams of metal to moles of metal, that's just simple stoichiometry. That's involving formula masses, and depending on which direction I'm going will determine whether I'm multiplying or dividing. Moles of electrons, in this particular case, this is the moles of electrons that's actually transferred during my redox reaction. And so remember, we've learned how to balance out our redox reactions, right? And so going from here to here, there will actually be a mole ratio that's involved here. And so I can either get it from the reaction, or if I'm looking at a specific half reaction, I will look at that standard reduction table, or look at the standard reduction reaction, and I can figure out how many moles of electrons are going from here to there. All right. Coulombs is that charge, and going from moles of electron, this is an important point here, going from here to here, this is where that comes into play, right? That 96,485 coulombs per mole of electron, you can see that that's what relates moles of electrons to coulombs. So I can actually multiply or divide there to convert back and forth, and we'll do some examples of these in class. And then the last one is actually just an equation, and what it does is it relates the number of coulombs. This is my amperage, right? And so that's my amount of charge per time, and then T is time, and T here in this particular case is in seconds, right? Because of the units of my amperage, it's coulombs per second. Time in Faraday's law, this particular equation is going to be in seconds. And so you have to watch yourself, because sometimes they'll ask your questions, hey, how many minutes will this take, or how many hours will this take? And you have to do that conversion, understanding that when I plug everything into coulombs, or I'm sorry, Faraday's law here, that it all needs to be in seconds, all right? Okay, so I know that was a lot. We'll get into some of these problems in class, and I'll show you just some general examples of how this information flows through. If you have any questions, be sure to come see me in tutorials and get them taken care of before we get to class. And otherwise, I will see you there.